Hey everyone, welcome. Today, we're going to dive into one of the coolest and most fundamental ideas in machine learning, clustering. It's all about finding hidden patterns in data.
You know, we are just swimming in data every single day. It's everywhere. But how do you actually make sense of it? I mean, how do you find the natural groups, the hidden communities, inside all that information? Especially when you don't have any labels or answers to start with.
And that right there, that's the big challenge. It's exactly what clustering algorithms were built to do, to find a little bit of order in all that chaos.
So, officially, clustering is what we call an unsupervised learning method. What does that mean? Well, it means we can basically hand a computer a giant messy pile of data with zero instructions and just say, hey, find the structure in here. It's kind of like dumping a huge bag of Legos on the floor and asking a friend to sort them by type without ever telling them what the types are. They have to figure it out on their own. And believe me, this isn't just some abstract, nerdy concept. You interact with clustering all the time. When an online store recommends a product, it's probably because they've clustered you with other shoppers who have similar tastes. Scientists use this very idea to discover new galaxies, and researchers use it to find crucial patterns in our DNA. It's everywhere.
So, how does this actually work under the hood? Well, let's start with the most famous clustering algorithm of them all, K-Means. If you want a good way to think about it, picture K-Means as a super fast, super efficient organizer.
The basic idea behind K-Means is actually pretty simple. First, you have to decide how many clusters you think are in your data. We just call that number K. Once you've picked your K, the algorithm's entire mission is to find the perfect center point, or centroid, for each of those groups.
And it does this with a really neat little dance. First, it just randomly plops K's center points onto your data. Then, it goes through every single data point and assigns it to whichever center it's closest to. Step 3, it moves each center to the average location of all the points that were just assigned to it. And then, it just does it again, and again, and again. Assign, update, until the centers finally stop moving. And that's the thing, right? That simplicity is its superpower. K-Means is incredibly popular because it's fast, it's pretty easy to get, and the results are usually straightforward. For a lot of problems, it works like a charm.
Now, with that kind of simplicity, you might be thinking, great, K-Means is all I'll ever need. But what happens when the data isn't so simple and well-behaved? What happens when the patterns get a little weird?
Yeah, about that. Turns out, the very thing that makes K-Means so fast and efficient, its core assumption, is also its biggest weakness. See, here's the catch. K-Means basically assumes that all clusters are nice, round blobs. It's looking for spheres of data. And when your data actually looks like that, it's perfect. But what if your groups are shaped like, I don't know, crescent moons, or maybe long, thin lines, or circles within circles? That's when K-Means starts to get really confused.
Just imagine that crescent moon data. K-Means is totally blind to that beautiful curved shape. It would just see a jumble of dots and try to force two big round circles on top of them. It ends up cutting right through the real patterns, giving you a result that completely misses the point and misrepresents the truth in your data.
And this is where we need a totally different approach, a different kind of hero.
So let's meet DBSCAN. If K-Means is the fast organizer, you can think of DBSCAN as the careful density detective.
DBSCAN has a completely different philosophy. Seriously, it could not be more different from K-Means. It doesn't care about finding centers. Not at all. Instead, it looks for crowded neighborhoods, areas where a bunch of data points are packed tightly together that are separated by empty, lonely spaces. It has its own simple vocabulary to do this. A core point is like someone in the middle of a party. They have a lot of friends nearby. A border point is on the edge of the party, but still close enough to hear the music. And then you have noise points. These are the outliers, the loners, way out in the middle of nowhere. This simple idea allows DBSCAN to brilliantly identify and ignore those pesky outliers that can mess up K-Means.
So what it does is it just connects the dots. It finds a core point, then looks for all its neighbors and their neighbors, and so on. It basically traces the cluster, following the dense path of points. And because of this, it can find groups of any shape, no matter how complex. Those crescent moons? No problem for the density detective.
So here's the crucial point. In machine learning, there's almost never a single best algorithm that works for everything. It's always about choosing the right tool for the job you have in front of you.
And this table just lays out the trade-offs perfectly. K-Means, our organizer, is super fast, but you have to tell it how many clusters to find, and it assumes they're all round. It's also really sensitive to outliers. DBSCAN, our detective, is a little slower, sure, but it can handle any shape you throw at it. It figures out the number of clusters on its own, and it's fantastic at ignoring noise.
So the biggest lesson here is this. Before you ever pick an algorithm, you have to get to know your data. Ask yourself, what does its shape look like? Are there dense regions? Are there outliers all over the place? Answering those questions first is the absolute key to picking the right method and actually finding the meaningful patterns hidden inside. And that leads us to one final thought. The next time you get a movie recommendation or see a targeted ad or scroll through your social feed, just stop and think for a second. What hidden groups are you a part of? What invisible clusters, discovered by algorithms just like these, are quietly shaping the world you experience every day?